In this video, we demonstrate how to continue Gaussian elimination and put a matrix not merely into row echelon form, but into reduced row echelon form. This process is called Gauss-Jordan elimination, and we will demonstrate this process via example. Referring back to a previous video, we put this matrix into row echelon form. And Gaussian elimination starts at the upper left and works down and to the right. The first thing we did was use the upper left entry to turn the 4 and the 6 below it to 0. We then moved down and to the right from this entry to this -3 and used it to eliminate everything below it. This is in row echelon form, but not reduced row echelon form. To be in reduced row echelon form, we need the leading entries to be 1. This leading entry is 1, but this is -3. Moreover, we need everything above a leading entry to be 0. This 2 above this leading entry isn't. To get row echelon form, we worked down and to the right. We're now going to start at the bottom right and work up and to the left. But when I say we start at the bottom right, I mean the bottom right pivot position. Now that this matrix is in row echelon form, we can read off the pivot positions, the first non-zero entries in a row. And the bottom right pivot position is this one. We need this leading entry to be 1. And here's where the row operation multiplying by a constant is going to be necessary. To make this leading entry 1, we multiply the second row by -1/3. What else did we need? We need everything above this leading entry to be 0. And we'll use the exact same process we used to eliminate numbers below leading entries during the Gaussian elimination. How can we get rid of this 2? By multiplying the second row by something and adding it to the first row in such a way that this 2 goes away. In particular, we have a 1 here. To turn it into -2, we multiply it by -2, and so we need to, of course, multiply the entire row by -2 and add it to the first row. So here's our new matrix. We've taken the bottom right leading entry and made everything above it equal to 0. Referring back to this part of the process, when we did the Gaussian elimination, we started with the upper left entry, made everything below it equal to 0, and then moved down and to the right. Everything above this leading entry is 0, so we're done with it. We move up and to the left. If there were any rows up here, we'd use this 1 to make everything above it equal to 0. Or if this were something other than 1, we'd turn it into 1, just like we did with this -3. In fact, though, we're done. Once we reach the upper row and our entry there is a 1, the matrix is in reduced row echelon form. Gauss-Jordan elimination can be broken into 2 parts then. We start with a system. We put it into row echelon form using Gaussian elimination, working down and to the right. Then we put it into reduced row echelon form, working up and to the left. This part is called the forward phase, and this part is called the backward phase. Let's close with a theorem. Every matrix is row equivalent to 1 matrix in reduced row echelon form. The take-home message from this: we can always perform Gauss-Jordan elimination. And when we do perform Gauss-Jordan elimination, if we do it correctly, we can only get one matrix. This is as opposed to Gaussian elimination, where two different people could correctly perform Gaussian elimination on a matrix and get two different matrices. In this video, we've demonstrated how to perform Gauss-Jordan elimination. First, we perform Gaussian elimination, working down and to the right. Then we work up and to the left, turning leading entries to 0 and eliminating everything above them. In most settings, at least in this course, we will be performing Gauss-Jordan elimination. We'll see that there isn't a lot of reason to just perform Gaussian elimination.